Welcome to lecture 25. In this lecture, I will talk about the equations of motions for the Schwarzschild solution of the equations of GR. We've discussed the Schwarzschild solution to the Einstein fields equations in lectures 22 and 23. The Schwarzschild solution is a spherically symmetric and static solution. The solution is for empty space, so recall that we set the matter tensor, the energy momentum tensor, to 0 when we found the solution, except possibly near the center within the Schwarzschild radius, where we said that there could be some mass in there. So outside the Schwarzschild radius Rs, for r bigger than Rs, the solution is simply that of empty space. Now, if we have the solution, one potential application of the solution is that for the gravitational field that, for instance, a planet creates in outer space. So the planet has to be regarded as sort of a source. So far away, in this case, much outside of the Schwarzschild horizon, the gravitational field will be given by the Schwarzschild solution if the planet is not turning and if the space-time is time-independent, so static. So the solution of the Schwarzschild metric is a solution that is a generalization of the Newton gravitational potential for a mass in outer space. Now, if we want to consider this as an application, we have in mind a planet, and we want to consider a particle in the gravitational field of that planet, so that would be a particle in the Schwarzschild spacetime, then we can ask, well, what trajectory would that particle follow if we sort of have this particular gravitational potential? If it was Newtonian gravity, the particle would just follow a trajectory that's given by the gravitational field of the planet, so we can figure this out fairly straightforwardly. However, the solution or the general relativity dictates that the particle trajectory is given by the geodesic equation. So we are led to find trajectories of a particle for the Schwarzschild metric, which would be generalizations or refinements, if you want so, of orbits in Newtonian gravity. As you can verify yourself fairly quickly, if we start with the geodesic equation for Schwarzschild, finding trajectories is hard to do directly. It's possible, but it's hard. So in this lecture, I will demonstrate an alternative route to finding such trajectories. And this alternative route employs conserved quantities that we get from the Killing vectors of the Schwarzschild spacetime, which we discussed in the previous lecture. So now let's review the Killing vectors for a Schwarzschild solution. Recall that Schwarzschild solution is static, so time independent, and it's spherically symmetric. This means that there are several derivatives of the metric tensor that vanish. The time derivative of the Schwarzschild metric vanishes. The derivative of the Schwarzschild metric with one of the spherical angles as well as the other spherical angle are also both 0. So what this implies is that we have at least 3 Killing vectors because there are 3 derivatives of the metric tensor with respect to coordinates that are vanishing. And we can look back at lecture 24 to identify what those Killing vectors are. For the time-like Killing vector, we have the following structure. This is just the Kronecker delta, mu, and t. So if you want to write it as a vector, this is the form that it takes. The Killing vector that is associated with this particular symmetry has a 1 in the direction of the angle theta, which is my third coordinate here. Remember that the coordinates are time, radial direction, theta, and phi. And finally, the third Killing vector is the one that is associated with the symmetry in the phi angle. So that is a Kronecker delta that has only a 1 in the phi direction. So these are our Killing vectors. Recall that for each Killing vector, there is an associated conserved quantity. And for the Schwarzschild solution, we can write the conserved quantities in the following way. So we have this contraction between the Killing vector and u mu, so the derivative of x mu with respect to proper time. Um, you can write this either with upstairs indices or with downstairs indices. Here I choose downstairs indices. And I've inserted a minus sign for convention. This time-lag killing vector, because it's delta, Kronecker delta mu t, only has an entry when mu is equal to t or mu is equal to 0. So then this is the combination that survives. So this is u0, which is dt by d tau. And I call this conserved quantity E for energy, because that's the conserved quantity that goes along with the time-lag killing vector. And as I said, the minus sign here is convention, because I want the energy to be positive. So furthermore, we have the second or third, depending on the counting, killing vector. The one is associated with phi here. The conserved quantity, again, is given by the contraction of the killing vector with the 4 velocity. So again, in this case, the Kronecker delta says that there's only one component of this killing vector that is non-zero. That's the one where we have the third entry here, or the phi entry here in the coordinates. And we will call this conserved quantity L, standing for angular momentum. There is a third killing vector that also corresponds to a conserved quantity. I will sort of consider this particular contraction here, and that is the one that is conserved. And for simplicity of the sort of subsequent discussion that I want to have, I want to set this constant, the conserved quantity, to be equal to 0. This will simplify our discussion when we talk about solving for, in particular, closed orbits in the Schwarzschild spacetime. So this is a particular choice for this conserved quantity. Okay. Oh, yes, I didn't say this. So there are lowercase killing vectors here, and we have upper killing vectors here. How do we go from or from upper stairs index killing vectors to downstairs index killing vectors? Well, they are metric. They are 4 vectors, and we can use the metric tensor to go from upstairs to downstairs indices. Explicitly, if we want to construct, for instance, the time-lag killing vector with downstairs index, what we have to do is write the killing vector with upstairs index and a metric tensor. And if we plug in the result for the time-lag killing vector of the Schwarzschild spacetime, this is just this Kronecker delta. So the Kronecker delta contracted with the metric tensor just gives gt nu. And this is a vector which has only a non-vanishing entry in the time-lag component nu, and it's the time-lag entry of the metric tensor. So this is the time-lag killing vector with low stair or downstairs index. We can proceed in a similar fashion for the downstairs index killing vector that is associated with the angular momentum. And in this case, we find it's equal to g phi mu, which in components sort of takes the following form here. So now that we have these two killing vectors, we can plug them into the conserved quantities, the energy here. So we need the lowercase killing vector for the energy, and we need the third component of the lowercase phi killing vector for the angular momentum. If we plug those in, then we find that the energy is given explicitly as the sort of combination, or this is essentially the time lag part of the metric tensor with a minus sign, and the derivative of time with respect to proper time for the energy. And for the angular momentum, we have this combination here. In addition, I said that the third conservation law is just a conservation law that says that the time derivative of the angle is equal to 0. This just implies that we can set the angle theta to be a constant. And again, for simplicity, I will make a particular choice for this constant. I will choose this constant to be pi over 2, with the idea that if I choose it pi over 2, this sine squared theta term here would just be equal to 1. So basically, all angular dependence then has vanished here. Okay, so changing gears a little bit, let's tried now to use these conserved quantities in the Schwarzschild metric to come up with something like an equation of motion for particles in the Schwarzschild spacetime. And I said that it's hard to do that from the geodesic equation directly. So what we're doing is a slight alternative. The alternative we'll use is we'll want to sort of relate the proper time increment, d tau, and the line element for any spacetime here. And this equation holds if it's a massive particle. The equation would not hold, for instance, if we were considering a particle that does not have any mass, such as a photon, because then this is a light-like particle, and the line element squared would basically be 0 and not equal to d tau squared. But for a massive particle, this equation holds. So now that we know that this equation holds, we can divide this equation by d tau squared, and we find that there is a condition that says that the contraction between the metric tensor and these derivatives here has to be equal to -1. This condition should be familiar to us, given that if we define the derivative of the coordinates with respect to proper time as the forward velocity, we find that this condition here is just the normalization condition for the forward velocity that we have talked about when we were discussing the energy momentum tensor, for instance. So u mu is equal to -1 is nothing else but the condition that the proper time is related to the line element for a massive particle. Okay, so backing up a little bit. So we know this condition here. We know that we understand physically what it means. It means that the forward velocity of a massive particle is normalized in this way. Now we can go back to this condition here and just write it out in components using the metric tensor. So this will have contractions that involves, for the Schwarzschild metric, GTT, GRR, G5phi, and so on. So if we write this out in components, we get the condition that -1 is equal to GTT dt by d tau squared, GRR dr by d tau squared, and so on and so forth, all 4 metric components. For the Schwarzschild metric, that's everything, because the metric is purely diagonal. Okay, so now that we have this, we can recognize that these terms, for instance, dt by d tau, sorry, there should be a d phi by d tau here. These terms here are related to the conserved quantities that we talked about earlier. So let me quickly back up. So we have our conserved quantities that relate dt by d tau to the energy, which is conserved, and d phi by d tau to the angular momentum, which is conserved. And we've set d theta d tau to 0, so that's also conserved. So we can use these conserved quantities, which come from the killing vectors of Schwarzschild, to plug this into this equation. And if we make these replacements, we find that this condition here becomes -1 is GTT, and this thing here is E squared over GTT squared, GRR dr by d tau squared. I've not modified this one. The theta by d tau I've set to 0, and d phi, again, note the typo should be phi here. D phi by d tau is related to L, so we have replaced this by L squared over G5phi squared. So clearly some of these terms here cancel. We can bring them to the other side using, for instance, the fact that, again, GTT is, so this is type should read GTT is -1 over GRR, and that's equal to this factor, or 1 over this factor A of R of the Schwarzschild metric. So if we make this replacement here and bring range terms on the other side, we find that this equation is equal to -A, this factor A of the Schwarzschild metric, is equal to -E squared plus dr by d tau squared plus A of R L squared over G5phi. So finally, if we look at G5phi, which is R squared sine square theta for the Schwarzschild metric, and we recall that we've used one of the symmetries to set theta as pi over 2, we find that G5phi is nothing else but R squared. And we can, again, simplify these equation that we were talking about in the following form. So now it is an equation that involves conserved quantities. So if you want some constants, that's E and L. It involves the second derivative, or sorry, it involves the first derivative of the radius with respect to proper time squared, and it involves the single function a of r. So basically what we found is a single ordinary differential equation that effectively acts as an equation of motion, radius as a function of proper time for a particle with a given energy E and a given angular momentum. Plugging in the explicit form of the factor a of r for the Schwarzschild solution, we end up with the following form of this equation here, which again has been simplified. So a of r sort of appears twice here, so that's why it looks like this. I just want to contrast this with the equations of motion for a particle that's given by the geodesic equation. So again, here, what you should note is that the corresponding geodesic equation here is much more complicated. It's sort of linking second-order time derivatives with first-order time derivatives in different coordinates. So we would have to disentangle, if you want, so this set of nonlinear differential equations. So it's hard to solve the geodesic equation directly. So by contrast, the equation that we found by using the Killing vectors of the Schwarzschild metric is much simpler. It's the form of a first-order differential equation, and we'll see that we can actually solve this equation in a much more straightforward fashion, and we will do so in the next lecture.